One thing that's nice about power series is that they behave a lot like polynomials. So for example, if we wanted to find the Maclaurin series for x cubed cosine of x, we could start with the Maclaurin series for cosine of x, which we already know. It's the sum from k equals 0 to infinity of -1 to the k power x to the 2k over 2k factorial. And if we wanted to expand that, we would get 1 plus x squared over 2 factorial, excuse me, not plus, because that -1 makes it alternating. So minus x squared over 2 factorial, x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, so on and so forth. And if we want to find a Maclaurin series for x cubed cosine of x, well, all we're doing is multiplying cosine by the polynomial x cubed. And as it turns out, there is no problem with just taking that x cubed and multiplying it on the inside of the of the power series. So we have x cubed -1 to the k, x to the 2k over 2k factorial. And then I can combine the x cubed and the x to the 2k by combining their powers. So a nice way to write this power series would be x to the 2k plus 3 over 2k factorial. And that's it. That's actually my final answer. It's all I had to do. Now I'll notice that I didn't really show it as a Maclaurin series. I didn't do all the derivatives that I normally need to do to find a Maclaurin series. But this is a power series that converges to x cubed cosine of x for all values of x, and it's not too hard to show that, well, if you have some power series that converges and there is a Maclaurin series, the power series that you know converges has to be that Maclaurin series. It's not hard to prove that. So all we need to do is just find some power series with this x minus 0 term here, and we're good to go. Okay, what would this look like in terms of the first few terms of that polynomial? Well, I could actually just take this x cubed and multiply it against those first few terms of the polynomial. So basically I'm just distributing that x cubed across all those terms, and I get x cubed minus x to the 5th over 2 factorial, x to the 7th over 4 factorial, x to the, 6 plus 3 is 9 over 6 factorial, so on and so forth. And these are the first few terms of this power series. And in fact, if you go ahead and just think about what you would get if you expanded this series, you would get this polynomial, the first few terms here on the right. Just for a nice visualization, let's go ahead and show that these do look similar. So if I pull up my graphing calculator here, here's what my graphing calculator says that x cubed cosine of x looks like. Notice that it kind of does some oscillating here out towards infinity. I just want to compare that with the first few terms of the polynomial we have here on the right. If I show what those look like, they overlap almost exactly. I mean, if you zoom in, after a while, you can kind of see where they are different, but from this perspective here, it doesn't look too bad. Now, of course, the cosine causes the red curve, the actual curve, to keep oscillating up and down out towards infinity. The polynomial does not do that. But for numbers between -2 and +2, it's a pretty darn good approximation. All right, let's go back and work another example. All right. We're going to find the Maclaurin series for exponential function of x squared. Okay, first of all, that's just simply the e to the x squared power. So what I could do is I could start with the fact that e to the x is k equals 0 to infinity, x to the k over k factorial, which expands to 1 plus x over 1 factorial, x squared over 2 factorial, which is just 2, x cubed over 3 factorial, which is just 6, That's enough terms there. Now, notice that in this case, we're not multiplying by anything, but we're composing things. So what we're doing is we're replacing this x with an x squared. So it's the composition of those two functions. And as you might expect, yeah, it's just as simple as composing. Here we replace the x with an x squared. So we'll do the same thing inside of here. Instead of an x, I'll write x squared to the k over k factorial. And I could simplify that by saying k equals 0 to infinity, x to the 2k over k factorial. And it's a power series. It doesn't, as long as we have an appropriate domain of convergence here, so in fact it's all real numbers, x works for this. And because we found a power series that converges, it has to be the Maclaurin series. So what does that look like when it's expanded? Well, on the right here, we could just imagine, what if we replaced every x here with an x squared? Here we have x squared squared. Here we have x squared cubed. I'll stop there. But that would just be 1 plus x squared, x to the 4th over 2 factorial, x to the 6th over 3 factorial. And that's the first few terms. Again, let's take a look at a visualization of what this would look like. On a graphing calculator, I can graph the exponential function of x squared, or e to the x squared power. And if I compare that, it's a pretty darn close fit. If I just have I have the first 5 terms here. Of course, if you have less terms, it's not quite as good as a fit. But with more terms, the closer fit that you're going to get here. All right, let's do one more example. We're going to find the Maclaurin series for x sine of 2x. So to do this, we'll start with the fact that sine of x is the series -1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. And we're going to use both of these tricks, multiplication and composition. So the first thing I'm going to do is use composition to get a 2x and all I'm doing is changing that x to a 2x. Everything else stays the same. Always do your composition first, because that way you don't have to, I'll show you in just a second what would happen if you didn't do it first. So here we can simplify this. This is, first of all, we'll take that 2 and bring it out. Yeah, I'll just write that as 2 to the 2k plus 1. And then up here, I still have x to the 2k plus 1 over 2k plus 1 factorial. And there is my series in the first few terms. Oh, I don't need that yet because that's not my final answer, is it? That's only sine of 2x. Now I need x sine of 2x. But all that says is, look, we're just multiplying by an x, which means all I need to do is add another x up here. So there's going to be x to the 2k plus 2 over 2k plus 1 factorial. All right, and there's my series. But if you need the first few terms, probably the best thing to do is to go back up here and write this out. This is x minus x cubed over 3 factorial, x fifth, 5 factorial, x seventh, 7 factorial. And all we did here was we replaced all the x's with 2 x's. So on and so forth. We have minus next. And then here, we just multiplied everything by an x. So on and so forth, which you could distribute if you wanted to, and then multiply out those cubes and fifths for however many terms that you need. Okay, but I mentioned you should do the composition first, because if I had done it the other way, this is what you want to avoid. So sine of x, but I start by multiplying by x. That's going to get me, well, it's just the same as sine of x, but instead of 2k plus 2, I get, sorry, 2k plus 1, I just add an extra x to the number to the exponent to get an extra x multiplied in. But now, you can't just compose. Oh, there shouldn't be an x squared. I want to compose in a 2x. And the problem is that I didn't change all of my x's. If I want to compose, I have to change all my x's to 2x's on all sides of the equation. I don't want to do that. I don't want a 2x sine 2x. I mean, you could work with that, but it's far easier just to do this process of composition first and then multiplication second. And here we get this power series, and it's a power series that converges for all values of x, because we started with the Maclaurin series that converges to sine of x for all powers of x. And if we find any power series that converges, it is the Maclaurin series, assuming it's centered at 0, which you can write that as x minus 0 if you want to convince yourself of that. And finally, let's take a look at the pictures for this. Here's what x sine of 2x looks like. And here are the first few terms of the polynomial I just generated. Notice that it works for a while up to about, negative 1.5. Really just negative 1 is all you can really work with here. It's visually speaking. Looks like it starts to get away from each other after that. But if we added more terms, we would get more of these oscillations matched in, and we would have a much better approximation.